Welcome back. Today we're going to be looking at section 5.3, the graphs of polynomial functions, and we are going to be looking at how the polynomial functions we learned about in 5.2 translate onto a graph, and how to look at the characteristics, look at the x-intercepts, the y-intercepts, the mins, the maxes, and then graph a full function. So let's get started. A lot of the things we're going to be talking about today are review from last week or last session in 5.2, but we're going to be applying it today into graphing our own functions, kind of like what we did as a preview in 5.2, off to the side. The first thing that we want to point out is there's two things that qualify a function to be polynomial. They cannot have sharp corners, and they have to be continuous. Smooth curves means no sharp corners, and they have no breaks or continuous. So the thing that's wrong in this case is that it's not a continuous graph, so it's not polynomial. That one's probably a piecewise, like we learned about in section or chapter 2. And this one looks just fine because it's smooth and continuous. It looks like it could be a polynomial function, perhaps a degree 3 polynomial. So we're going to look at these and say, okay, are these polynomials or not, or possibly polynomials or not? And then if not, what could they be? So this first one, it looks smooth, no sharp turns, no asymptotes. Good to go. We could even say the degree is potentially, we see 1, 2, 3 turnarounds, so the degree could be 4. Makes sense too because they're going in the same direction with the end behavior. So degree 4 question mark. Maybe it's 6. Can't be 2 because there's 3 turnaround points. But we know that those turnaround points indicate that the degree is at least 4. Maybe I'll write that. At least 4. The second one is not, because you should know from looking at those toolkit functions, this is more like the absolute value. Third one looks good to go, and it looks like it could be degree of greater than 3. And then this last one is not, it looks more like a piecewise, because we've got a condition here where the function changes. Even though it looks like it should be smooth, it's not because of that, it's not continuous. It doesn't continue at whatever x value this is. There's a break in the graph, and it's not continuous. So this try it one, what they want us to do is they want us to look at this graph, which is kind of hard to zoom into, but look at this graph and see if we can determine the y-intercepts and the x-intercepts. I apologize for the blurry graph. If you want to graph this function in Desmos or online somewhere in some tool, you could do that to maybe look at it a little better. But if I zoom in, it looks like we've got a intercept at that green point, an intercept at that green point, which is -5, an intercept at 2, and an intercept at 3. Looks like each square is about a quarter of a space, or a quarter of a unit. And this one's at 0. And so we've got 4 x-intercepts. So the x-intercepts look like they're -5, 0, 0, 0, 2, 0, and 3, 0. And then the y-intercepts, there's only one y-intercept, otherwise it wouldn't pass the vertical line test, wouldn't be a function. Looks to be 0, 0. A lot easier to do when you're looking at a graph than if you had to solve it yourself, though you could attempt to solve it by factoring out some numbers and seeing, you might get into a cubic function territory after factoring out that x though, and that might be a little scary without some of the tools that we're going to learn later in this class. So let's keep going. Oh, that would definitely be x. Yeah, that's what it would end up being, though. That's a hard function to factor because it's a cubic function. With not a lot of grouping possible. All right, we'll keep going. We'll say use the graph of the function, that it gives us the degree of 9. And remember, if it gives us the degree, we know that max turns, or minimum, the max turns is n minus 1 or 8. Can't turn more than 8 times. To identify the function and their multiplicities. We'll talk about multiplicities as we explore this try it. So the first thing we want to do is we want to identify the zeros. I'll do that in blue. We got a 0 here, so I'm going to write it over here in this nice little table that says zeros. This new word, multiplicities. And then this other new word, which is bounce or cross. And because we have the graph, we'll get to observe whether it bounces or crosses without having to know based on the multiplicity. So we've got 1 right there, and it looks like that's at -5, 0. Got another one at -1, 0. Got another one at 3, 0. And that looks to be all of the x-intercepts. And so now what we're going to do is we're going to establish some multiplicities. We're going to say, okay, if we were to zoom in really close to those zeros, what could that graph look like? And so if you're looking at this function, and you're looking at that graph and you're thinking, that is definitely an odd function because it goes down on the left and up on the right. It doesn't look linear because it has that weird little curve or change in concavity. And so I'm going to say at that first zero, our multiplicity could be 3, could be a cubic function, could be 5, could be 7, could be 9, but really it couldn't because our max degree is 9 and we have 2 other zeros. And so I'm going to go ahead and get rid of the 9 and leave the other 3 options as we explore more. All right, if we zoom into this next one, looks kind of like a squared function, right? It looks kind of like a parabola. If we zoom in right here and look at that section, so we know that the multiplicity could be 2, could be 4, could be 6. I'm thinking it's not going to go much higher than that. And then the next one, we look at this, and we see, oh, it looks like another parabola, but a little wider, right? And so we're going to use the toolkit functions that we know to kind of draw some context clues and say, well, if the 0 at 3 has to be wider than the 0 at -1, then it can't be 2. And maybe our best bet's going to be 2, 4, and 3. And if we add those numbers up, if we add those multiplicities up, because we only have 3 solutions, and remember that degree told us we could have had up to 9 solutions. If we add 3, 2, and 4 up, we should get 9, which means our degree is 9, and that seems to be the best option. And one last thing to note, if you scroll up here and look at it, talk about multiplicities, they talk about crossing at odd and evens touch or bounce. A way that I've always tried to remember it or taught to remember is remember this acronym EBOC or COBE if you turn it backwards. And what that's saying is even always bounces or touches. And this book uses the word touches. Both are fine. And odd always crosses. And so we can look at the first function and we can say, oh, it crosses the x-axis. So it's odd, so it crosses. The second one is even because it's 2, so it bounces. And the third one is even, so it bounces. And that is what happens if we look at the graph. A really important thing to think about is this multiplicity has nothing to do with the coefficient of the 0 or x-intercept and has everything to do with the exponent. The multiplicity has everything to do with the exponent, that p right there, and nothing to do with the coefficient. Sometimes it's easy to get them mixed up and look at the coefficient and say, oh, it's got a multiplicity of 2 because there's a 2 out front. We're looking at the exponent of each x-intercept, or the exponent of each 0. All right, there's another reminder for end behavior. We went over that in detail last section, but if you want to go back and watch that or look at this chart to remind yourself a little bit about end behavior before we fully graph a function. Now this is exciting. This is like the full applying everything we've taught in this class or in this polynomial section to graph a function. So the first thing we're going to do, I'll follow their instructions pretty close, is find the intercepts. So we have an x-intercept at 0, 0 from that red one. We have an x-intercept at 1, 0 from that blue factor. And we have an x-intercept of -3, 0 from that red, or the orange factor. So these are our zeros. So we're going to go ahead and plot them on the graph. 0, 0, 1, 0, -3, 0. All right, and what else do we know about these? Not a lot. We know their multiplicities. So maybe we can make that same table and say, okay, well, what about their multiplicities? Well, we could look at the red one and say, oh, what exponent is above that x? Be careful. There's an invisible 1 hanging out right there. So you got a multiplicity of 1 for the red one, a multiplicity of 4 for the blue one, and a multiplicity of 3 for the yellow one. And that's going to tell us, if we remember that EBOC, even bounces, odd crosses. So odd, cross, even, bounce, odd, cross. Now we've got the behavior. So we got the multiplicity and we've got the behavior. All right. Next thing we should probably try to find out is the end behavior. So we found out the intercepts. I skipped step 2 for a second to check for symmetry because I wanted to go ahead and find, while I was working on the intercepts, the multiplicity and the behaviors, which we did. I wanted to determine the end behavior. I wanted to determine what happens at the ends of the graph. And remember, to look at in behavior, we only look at that leading term. So we're going to look at the very leading term, which is going to be a little tough to pull out of this function. But remember, we can do it in a little sneaky or shortcut method when we have a fully factored function. We're going to take that first a value, that a that's out front. We're going to say the in behavior, or the leading term, is going to be 1/4. And then we're just going to count how many x's we have in our graph. Looks like we have 1 plus 4 is 5, plus 3 is 9. So we're going to have x to the 9. Nope, that's 8. 1 plus 4 is 5, plus 3 is 8. So our leading term is 1/4 x to the 8. And that's going to tell us everything we need to know about our end behavior. We know it's even. So what do I mean by even? I mean that 8 is even, right? This is not the multiplicity. This is in behavior. Different topic. Because that 8 is even, we know it's either happy or sad, but it's parabolic at the ends. So it's going in the same direction at the ends. And then because this 1/4 is a positive number, that means it's happy, like a bank account or like a smile. So we can get rid of the sad one and we can say, because it's positive and because it's even, we've got a happy parabola at the ends. So what I can do, which is kind of fun, is we can go ahead and go to the ends and go straight up, because we know at the very end of this, it's going to be a happy parabola. And we know that because if it were to turn around again, we'd hit the x-axis again, and we don't have any other intercepts to work with. And now that we have this, we can go intercept by intercept and look at, does it bounce or cross? And so if we look at 0, or let's look at -3 first. -3, it says it crosses. So we can go straight through and cross. And then what happens so now we're underneath the x-axis. So we're definitely going to have to turn around at halfway. And then what's going to happen at the top? When we get back to 0, 0, we're going to cross again. It's pretty cool. Ooh. And then I can tell you without even looking, because we're on the same side of the graph right here and we have to cross, we're going to bounce off of this 1. Let's go check and see. We go and look at the 1. It says bounces. That makes sense. So we're going to just bounce right off of it, and it's going to look something like that. And that is how we apply the multiplicities, the zeros, the y-intercept, and the end behavior to graph our function. That last step says ensure that the number of turning points doesn't exceed 1 less than the degree. So we could just double check on that. And we could say 1 turning point, 2 turning point, 3 turning point. That does not exceed 8, which was our degree. So we are A-okay with that one. All right, I'm going to hop over the intermediate value theorem for the sake of time so we can keep graphing some of these functions and go on to something a little prettier, which is to write the formula for the function. So we got ourselves a function and saying, hey, I need you to write this formula or a potential formula for this based on everything you know. So the first thing I'm going to do is I'm going to say, well, I know my zeros. I know I have a -1, which means I'm going to have a x plus 1 term. I know I have a 2, a positive 2, which means I'm going to have an x minus 2 term. I know I have a 4, so I'm going to have an x minus 4 term. And now we're going to try to go gauge those multiplicities as best as we can. Even though sometimes it might be a little tricky, we're going to look as close as we can at each of the graphs, zoom in and say, what shape does that kind of look like? Kind of looks like a parabola. It's following a parabolic path. And so our multiplicities are either 2 or 4. The 4 one is usually a little wider at the base, kind of looks like the short and squatty parabola. And so my guess, just from context clues, is going to be 2. But let's keep going to see if we can get this degree. We'll do the same thing over at 2. We know that this is odd because it's going like a snake and it's crossing the x-axis. So guess 3, guess 5. The reason I didn't guess 1 is because you see this change in concavity, you see this snake shape. A 1 would be like a linear function, and we're about to see that on the next one. When something looks perfectly linear at the x-intercept, we can give it a 1 multiplicity, an m of 1. All right? And so I'm going to go ahead and make a guess, again, a guess at 3, just to see, and throw those in and see what happens if we get our, if we apply those to our factors. We will plug and chug some numbers and see if we got it right. So at -1, so we had a 2 multiplicity. At 2, we said we had a 3, and at 4, we said we had a 1. That means our degree would have been 2 plus 3 is 5, plus 1 is 6, which means max turns was 5. Did we exceed our max turns? We got 1 turn, 2 turns, 3 turns. Nope, we're good to go. All right, So we're only missing one thing now from this whole function, and that is that term out front that's always out front that always has the same variable, a. And that a is just going to be the way that our function is shifted, the way that it's compressed or stretched vertically. So here's what we'll do. We'll pick a number. There's probably one good number on this graph that they give us to solve for a. So if you look at the graph, we've already used 3 numbers. And I see pretty much one solid number that we can use as we go and solve for that a value. Look down here at the point 0, -4. That y-intercept is going to help us solve for a. So what we're going to do is we're going to plug in the x1 and the y1, or the x1 and the f of x1. Let's see if we can't get a reasonable a value. So f of x is -4. That's the y value. Is equal to, leave a alone because that's what we're solving for. And then we're going to plug in 0 everywhere we see an x. Oh, I wrote x. I meant to write 0 -4. So we've got -4 equals a. 1 squared is 1. -2 cubed is -8. -4 to the first power is -4. So we've got -4 equals a times, remember carefully through negative signs, 32. Which means if we divide that, we'll get a equals -4 over 32, which is -1. If we divide by 4 on both sides, divided by 8. So we got ourselves an a value of 1 over 8, and we can complete our function. Double check on that. Make sure we're good to go. Yep. So f of x equals, use that a value that we just solved for using the y-intercept, and put those x's back in. 2, x minus 2 is 3, x minus 4 to the 1. We got ourselves a function. Awesome. If you want to go hop onto Desmos and check that, you can plug that into Desmos and see if we don't get the same maximum right here, about 4.25 or something. We'll check some special points that you can see the intersections and see if those turnaround points look about the same. All right, in a different section, we've already talked about local max and local mins, and then global max and global mins. So I'm going to hop down here and, using Google or Desmos, find the maximum and minimum values on an interval. Note, we're not going to use technology often in this class. We prefer to do everything by hand, like we just did. But in order to look at graphs, kind of like we printed screen up here and gave you a graph that you could solve from, sometimes it's good to just see a picture and say, oh yeah, I could determine it with a picture if I had one. So I might go ahead and do that for us. Just to give us one more example of finding maxes and mins. So what I'm going to do is I'm going to go to Desmos. I prefer Desmos as a graphing function because it's easy to move around and see special points and click on it for points. So f of x, y equals -0.2 x minus 2 raised to the third. Then we've got x plus 1 raised to the second. And then we've got x minus 4. All right, I got my Desmos. I'm going to drag it down here so we can see it. It's going to be a little hard, but that's okay. Put that over there. And we'll put the notes back over here. And we will see if we can determine what it asks us to find, some maxes and minimum values on the interval. All right, well, if we look at this graph right here, see we've got a local max. So I might say we got a local max at -1, 0. And you can probably look around and find another local max by clicking on it. Oop, ooh, that's a tall local max. Is that the full point? Yep, we got ourselves another local max at a real ugly number. Another local max at 6.951. Got ourselves a local minimum down here, it looks like. Local min at 0.093, comma, -6.474. Like I said, we're not going to use technology a lot, but sometimes it's good to look at a graph and see if we can determine a few key features about it. What else does it say to do? It says find the maximum and minimum values on the interval -1 to 4. Oh, it only asks us to look from -1 all the way to 4, which is what we did. That's just excluding the 2 end behaviors that go all the way down right there on the ends. So we found local maxes, local mins. We can find the absolute max. Absolute max definitely looks to be way up there. So we can just make a note that says absolute max is at the exact same spot. So that is one of the local maxes. Or, whoops, wrong one. Absolute max occurs at that spot we already talked about, which was 0.65, 3.573, comma. That is a local max and an absolute max because it's the tallest point it goes to right up there. And then we've got a local max down here, but it's not absolute because it doesn't go all the way up. And then we've got a local min way down here. And because it doesn't go any lower than that, remember we're excluding the other sides, we've got an absolute min at the exact same spot. Awesome. Now, that's pretty much a summary of all the key features of the graphs of polynomials. Remember, they have to be smooth. Remember, they have to be continuous. Remember that you can analyze some of the features about them using the x-intercepts, using the y-intercepts, using the multiplicities, which is the new thing for this week, which is allowing you to know that evens bounce off the x-axis and odds cross the x-axis. And then based on end behavior, you can graph your entire function, no matter what the polynomial is, no matter how long or short it is. Thank you for watching so far. Remember to be reviewing the videos from lessons past and working on the practice homeworks as you prepare for our Chapter 5 test coming up. Thank you for watching, and I'll see you next time.